Welcome to Quantum Tech Sage. Today, we're looking at a claim that sounds almost too dramatic to be true. OpenAI says an internal version of its next major model, Astra, produced 10 new results across mathematics and theoretical computer science, and that the successful solution tokens would cost roughly $2,000 at current Sol API rates. That does not mean 10 equal-sized famous problems were neatly solved for a $2,000 total bill. The real story is more precise, and honestly more interesting. A general reasoning model generated research arguments. Humans prepared the manuscripts with the model, and the model then formalized the results into machine-checkable lien certificates. 3 numbers explain why this announcement is getting attention. First, 10 results, covering fields from high-dimensional geometry to quantum complexity. Second, roughly $2,000, but specifically as a token cost estimate at Sol API rates. Not the full cost of training Astra, running the lab, or reviewing the work. Third, lien certificates. A proof assistant can check whether each formal deduction follows from the stated assumptions. That makes this very different from a chatbot producing a persuasive-looking paragraph. The headline is enormous, but the supporting package is also unusually concrete. Manuscripts, reasoning walkthroughs, and formal proof files. So, what exactly is Astra? OpenAI describes it as the company's next major model. And these results came from an internal version that is not yet a normal public product. The important point is that this was not presented as a narrow theorem-proving engine built for one benchmark. OpenAI says it evaluated a general model on open research problems during development. That matters because research mathematics is not just calculation. The system has to choose a direction, abandon dead ends, invent useful intermediate statements, and hold a long argument together. The paper shown on the slide is the 249-page collection released with the announcement. The workflow has 3 distinct stages, and keeping them separate prevents a lot of confusion. Stage 1 is discovery. Astra generated the mathematical arguments. Stage 2 is exposition. Humans used the same model to prepare those arguments as readable manuscripts. Stage 3 is formalization. The model translated each argument into lien, a proof assistant that checks the logical chain. This is not a fully autonomous publishing pipeline. Humans still selected problems, shaped the final manuscripts, and assumed responsibility for correctness. But it is also more than human researchers using AI as autocomplete. OpenAI explicitly says the mathematical arguments themselves were generated by the system. The 10 results are not all versions of the same trick. They spread across at least 8 research areas. Geometry includes sphere packing and Earhart's volume conjecture. Coding theory includes binary and spherical codes. Complexity theory appears in arithmetic circuits and quantum parallel repetition. Algebra and analysis show up in non-sophic groups and Connay's rigidity conjecture. Lattices connect to the closest vector problem and post-quantum cryptography. Extremal combinatorics includes multicolor Ramsey numbers and 2 Erdos problems. That breadth is part of the signal. Astra was not merely tuned to dominate one narrow mathematical niche. Let's translate the first cluster. In high-dimensional sphere packing, the collection reports the first improvement since 1978 to the general packing exponent. For binary and spherical codes, it claims exponentially improved upper bounds across the parameter range. Earhart's volume conjecture is presented as solved in every dimension, identifying the sharp maximum volume under its lattice point condition. And in arithmetic circuit complexity, the work gives new lower bounds for computing the permanent. These are not school-style answers. They are improvements to the limits mathematicians can prove about entire families of objects as the dimension or input size grows. The remaining results move even further across the map. Astra constructs an explicit non-suffix group addressing a central open question in group theory. It disproves Connay's rigidity conjecture by building different groups with the same von Neumann algebra. It proves an exponential parallel repetition theorem for general 2-player quantum games. It strengthens hardness for the closest vector problem, a lattice problem connected to post-quantum cryptography. and in extremal combinatorics. It advances multicolor Ramsey numbers while resolving Erdos problems 146, 180, and 183 through new graph constructions and bounds. A benchmark score can hide a lot. A 249-page research collection cannot. OpenAI released full mathematical manuscripts, a separate set of discovery notes, and formal lien certificates. The abstract alone lists the 10 claims in technical language, while the later chapters develop proofs, definitions, and references. This still does not guarantee that every claim will survive expert scrutiny, but it creates a public object that specialists can inspect line by line, reproduce, criticize, and extend. The evidence is therefore closer to a research release than a product demo, and that distinction is essential when evaluating a claim this large. Now the $2,000 figure. It is striking because it suggests that the marginal inference needed to find the successful solutions may be cheap compared with the value of expert research time. But it is not the total economic cost. OpenAI expresses the token volume at Sol API prices because Astra itself is internal. The estimate does not include model training, failed research directions outside the counted runs, infrastructure, human preparation, formalization review, or future peer review. The honest takeaway is not that 10 theorems cost exactly $2,000. It is that once a capable research model exists, the additional compute for successful discovery may be surprisingly small. Lean changes the credibility equation, but it does not eliminate judgment. A lean certificate checks that a formal theorem follows from formal assumptions using accepted rules. It can expose missing steps and prevent many subtle logical errors from hiding inside fluent prose. What it does not automatically prove is that the formal statement perfectly matches the original open problem, that the assumptions are appropriate, that the result is genuinely original, or that the mathematics is important in the way the announcement suggests. Those questions still require domain experts. Think of Lean as a very strict proof checker, not a replacement for the mathematical community. The strongest reason to take this seriously is the combination of artifacts. Detailed manuscripts, reasoning walkthroughs, and machine-checkable certificates. The strongest reason to remain careful is timing. These materials were released only days ago, and independent experts need time to check whether each formal statement captures the intended conjecture, whether the novelty claims hold, and how the work relates to prior literature. OpenAI also acknowledges broader questions about attribution, access, and the effect of AI on mathematical practice, pointing to debate within the community. The right posture is neither dismissal nor instant canonization. It is unusually interested scrutiny. If the results hold up, the economics of research may be changing in 4 ways. Exploration gets cheaper because a model can test many proof directions quickly. Verification becomes more scalable when successful arguments can be formalized. Small teams gain leverage because they can cover more technical ground, and research portfolios can widen. Instead of betting months on one path, scientists may run many structured investigations in parallel. None of that removes the need for experts. It shifts expert time toward choosing worthwhile questions, checking assumptions, interpreting significance, and connecting new results to the rest of the field. The real breakthrough may not be a single theorem. It may be the feedback loop. Generate an idea, turn it into a rigorous argument, formalize it, find the weakness, and try again. Astra's 10 results are an early, high-stakes test of that loop. If independent mathematicians validate the work, this announcement will mark a transition from AI that solves difficult exercises to AI that can participate in creating new knowledge. The most useful question is no longer, can a language model do math? It is, how should humans organize discovery when reasoning, verification, and iteration can all be accelerated? For similar informational content, please like, share, and subscribe. Quantum Tech Sage.